So this is a pleasure to introduce Paul Blanche, who is making his PhD with Hélène Lapin-Gadard here in Bordeaux, and that will complement the talk from Cécile about AUC.
Hello. So this is a joint work with Cécile and also with Lucie, Hubert, and my PhD advisor, Hélène. So the title of the talk is slightly different from the title of the program, but the topic is the same. So it's about quantifying and comparing the dynamic predictive accuracy of joint models in a specific case where we have a longitudinal marker and also time to event with competing risks. So just heard this morning, with joint model we are able to do a lot of different dynamic prediction, and there are a lot of different ways of doing that. So our interest in this work was to think about how can we evaluate and compare this kind of dynamic prediction. And this work is mainly motivated by two large cohort data of elderly people. So the first one is the practice cohort, including almost 3,000 subjects, and the second one is the 3-city cohort, about 4,000 subjects. And for the subject of this cohort, we are interested in prediction of dementia, accounting for the competing risk of death without dementia, and we would like to use repeating measurement of some cognitive tests that are strongly correlated to the risk of dementia. And more specifically, the statistical goal is to make inference with some things that we call some dynamic accuracy curves. So we want to estimate dynamic accuracy curves, and we want to make inference, and we want to go to different regions and test for this curve. So we have the so-called competing setting because at the other one our subjects are healthy and they are at risk of two competing events. Either they can get demented or they can die without dementia. So for the notation we have time t, the time to event, and eta, the type of event. The main event is the event 1, dementia is the competing event. Event 2 was the dementia. So of course we are in a workshop in cancer. So when we talk about dementia, it's slightly different, but the topic is quite close from a statistical point of view. The kind of data is the same because on cancer you can be also interested in the death from a specific cancer, and you also have to account for the death from another cause. So this is very similar. So we are interested in dynamic prediction, so it was very nicely introduced 2 minutes ago. So here we have the follow-up time, and we have a cognitive score. For us, in this example, this is a minimum task examination. So we have a first measurement at baseline at the enrollment, and then 1 or 2 years later, we have another measurement of this function, and 1 or 2 years later, we have a third one, and so on. And so at a given time that we call the landmark time, let's say after 4 years, we have an idea of the cognitive evolution of the subject, and we would like to use this idea about the cognitive decline to make dynamic prediction. So we want to fix a time horizon t here to make the prediction. We want to evaluate the probability of the event of dementia between the landmark time s and the time s plus t. We talk about dynamic prediction because in this talk the landmark time s will vary, but the time horizon t will be fixed to 5 years. It makes sense for our calculation. So let's take the implementation. So we have an event type and time to event and event time, t and eta, and one of the most important quantity in this talk is the indicator of disease occurrence within the time window. So the indicator of experiencing a dementia between time s and s plus t. And so we are interested in dynamic prediction denoted by p, right, in this talk. So this is the probability of experiencing a dementia between s and s plus t, given that the subject is at risk of dementia. So dementia free and alive, and all the repeated measurement of the marker and some baseline covariance. And Dimitri's and Cecil have already explained that there are some formulas to deal with this probability. So in this talk, we assume that we have already fitted a joint model, and when you have fitted this joint model, then you have a full parametric model for the joint probability distribution. So you have some parameters that are estimated, and from this estimated parameter, you are able to compute this prediction. So when we are interested in predictive accuracy, we are interested either in discrimination or prediction error. So for discrimination, basically the idea is does the higher predictive risk really mean that the subject is more likely to experience the event? So in other words, it means how often we observe a high predictive risk for a subject that experiences a dementia between time S and S plus t, and how often the predictive risk is higher than the predictive risk of a subject that do not experience a dementia. That means that either the subject died dementia-free between time S and S plus t, or is alive and dementia-free after time S plus t. So to formally define this, this is the area under the work curve. So within the work curve terminology, and the subject experiences an event is very often called the case, and given free is the control. So the around the curve is just the probability that the case has a higher predictive risk than the control. And of course, this is among the subjects at risk at time S at the moment time. So for the interpretation, this is the higher the better. This is a discrimination measure, and this discrimination measure does not depend on the incidence in the time window S is present. So we are also interested in prediction error. So in brief, the idea is to answer the question how close are the predicted risk TIST from the true underlying risk of even given the available information. We will of course use the joint model, that is a working model, and so we are not sure that the risk we are actually estimating are very close to the true risk. So we would like to assess this. And more formally, the Breuer score will do this. So the Breuer score is defined as the expected mean square error. So this is just the mean square error between the observation, whether or not the subject experienced the main event within the time window, minus the probability and then the square. And so for the interpretation, the lower the better, because the mean square error. And so in brief, it's approximately, for the interpretation, this is the sum of the square bias term plus a variance term. And an important thing is that this criteria evaluate both discrimination and calibration, but it depends on the incidence in time S. So in fact, we are interested in right sensor data. So basically, the right sensoring issue is that we are mainly interested in the indicator of having an event or not within the time window S plus t. And for some subjects, when they are uncensored, then it's clear that we know this indicator statue. For subjects censored after the time S plus t, then again we know the indicator, the value of the indicator statue. But for subjects censored within the time interval, between time S and S plus t, the statute is unknown. So this is a problem we have to account for. So for the notation, we note that delta t is the observed time, the sensor time. Delta is the indicator of censoring, and tilde eta the observed code, the sensor code, and by the dynamic prediction process. And to account for the censoring, then we use inverse probability of censoring weighting estimator. So basically the idea is that if we observe a subject of a dimension between time s and s plus t, the weight will be equal to 1 over the probability of surviving beyond the observed time. If a subject is known to be event-free after time s plus t, the weighting will equal to the estimated survival probability of the censoring at time s plus t. And if the subject is censored within the interval, then the weight is equal to 0. And because we do not observe the true event indicator, we use a proxy. This is an observed occurrence indicator. So the value is 1 if we actually observe a dimension within the time window SSP, and 0 otherwise. And for instance, to compute the bias score, then that's quite easy. We just use a weighted sum. So we estimate the expectation by a weighting mean with the inverse probability points. And for AUC, there are a similar formula. So the nice thing with this kind of estimator is that we have nice results. So they are consistent and they are unbiased and they are smooth in the sense that they converge at the usual root n consistency rate, and the difference between the estimate and the true value can be written as a sum of IID terms. And in fact, this is a quite useful result, because as soon as you know that the IID terms are zero mean IID terms, and as soon as you are able to easily estimate these IID terms, then you can compute almost every inference procedure that you want, as you will see. So from a practical point of view, from the applied mathematician point of view, this is very useful. So the proof consists in 3 steps. So the basic idea is to use the Martin-Gans theory of the Carbon-Layer estimator to account for the variability of the weights. And then you want to connect the variability about the weights to the variability of the estimator. So to do this, you use some Taylor expansions. And as a result, you have a sum of non-IID terms. So to rewrite this big sum as a sum of only n IID terms, we use a trick from new statistic. This is the adject projection principle. And so, in practice, what is nice is that for a fixed landmark time, then we know that the estimator is asymptotically normally distributed. So as usual, that's very easy to compute confidence interval, wild type confidence interval, so the estimate plus or minus the standard deviation. And to estimate the standard error, then you just have to use the estimator of your instant function and just to use the empirical standard deviation, standard error estimator of the estimating IID. So this is quite easy to compute. But because we are in the joint modeling approach, we are interested in dynamic prediction for a lot of different landmark times. So we do not want only inference for a single landmark time, but we also want to make inference for the whole curve of the dynamic prediction accuracy when the landmark time S varies, and to do so, we want to compute so-called confidence band. So this is the band that contains the whole curve for all the landmark times. And to do so, we also use a kind of one-type interval, but we have to correct for the simultaneous inference by computing a specific quantile. And to compute this quantile, you can use a simulation algorithm in the idea of being a collaborator. And basically, it consists in using the IID terms. So you generate some univariate standard unknown variables, and then by taking the slope over a normalized statistics over the whole landmark time, then you are able to compute the appropriate function. So in practice, we want to compare two dynamic prediction tools. So first, we are interested in testing a difference in predictive accuracy. So for instance, we are interested in testing whether or not the two dynamic AUC curves are equal or not. So here, theta denotes either AUC or the Blanche score. So to test whether or not the curves are equal, then you just need to compute the confidence zone of the difference of the two curves, and then by observing whether or not the zero function is contained within the confidence zone, then you can test this hypothesis. But sometimes you want also to know whether or not the dynamic predictive accuracy curve, the AUC or Blanche score, is always above the one another dynamic prediction tool. And then the idea is the same. You can compute the confidence of the difference, and then to be sure with a certain confidence level that one curve is uniformly above the other, then you just have to observe whether or not the confidence range of the difference overlaps the zero line. So we have our multi-rating data. So the first raw data is our training raw data, the basic data with 3,000 subjects. So we use this work to estimate the two joint models. So one will model the time to event. So the time to event, the dementia occurrence, and test dementia-free occurrence simultaneously jointly with the relative measurement of the minimum time state examination. That is one of the most famous cognitive tests. And in brief, this is a cognitive test that evaluates global, this is a global index of cognition. And we have another relative marker that is the ISAC score test. And this cognitive test in brief evaluates speed of verbal production. So the goal of the application is to compare two different joint models. One is based on the relative measurement of the minimum time state examination, and the other one is based on the relative measurement of the ISAC score test. And after administrating these two different joint models, we'll look at the difference in predictive accuracy on the validation cohort, the 3 cohorts with about 4,000 subjects. So to do so, we use a joint pattern class model, so it's already presented by Ceci. So in brief, the idea is that you have your time to event and type of event, and you have your marker trajectory, and both are there, and they are linked by the pattern class, so the population is divided in a subgroup that you do not observe, and this is how you link the two subunits, so the time to event and the marker trajectory. And as baseline covariates, in addition to the multi-measurement of the two cognitive tests, we will use age, education level, and sex. So in our application, the right censoring and the computing risk are really important because, as you can see in this plot, this is a descriptive graph for the three cities sample, so our validation sample. And as you can see, here the number of subjects in the y-axis, and here is the landmark time at which we are making predictions. So basically every 6 months for a fixed window of prediction time horizon of 5 years. And within each window of prediction, then the proportion of subjects that are censored within this window in red in this graph is quite high. and the proportion of subjects that experience a test dimension-free continuous in that window is also found high, so we have to account for both censoring and continuous issues. And here are the results. So here are the normal time at the parametric prediction with the AUC curve, and so you have the estimated AUC curve and the pointwise confidence interval, and as you can see, then the exact score test performed better than the minimum time examination. So the dynamic prediction from this test are better, and the discriminant accuracy are quite high. I mean, between 80 and 90%. That's fair. And when we want to compare these two curves, then we compute the difference in AUC of these two curves. And as you can see in this graph, then because the bound of pointwise confidence interval do not overlap the zero line, then for all landmark times the difference is significant. And because the confidence limit of the whole curve, the simultaneous confidence mode, do not overlap the zero function, then the simultaneously over all the landmark times, then this tells us that the exact score test is uniformly better than the normal expectation for discrimination. And here are the results for the wire score. So the curves are quite close. Even if there is a difference, but the difference is not very significant. It's not significant at all, in fact. And in fact, the first time I saw this graph, I was very disappointed. And one problem with this graph is that it's really difficult to interpret, because with AUC the scaling is easy to understand, but with the Bordeaux score the scaling is not very easy to understand. So one alternative could be to fix for fixing the difficulty, so scaling problem, and that is partly due to the fact that the Bordeaux score depends on the cumulative incidence within the time window, and also to fix the interpretation difficulty that this increase or decrease in Bordeaux score is not explainable when time S varies because of the cumulative incidence changes. Then we can define an explained variation criteria. So basically, this is just the Bordeaux score of the dynamic prediction, but divided by the Bordeaux score of the null model. It means that the Bordeaux score of the model predicting the same risk for all subjects. So it predicts the marginal cumulative incidence within the time window for all subjects. For this risk can be easily be estimated by some Olin-Johnson estimator. And with this criteria, it's easier to interpret, because then it's clear that okay, this is the area is better, and the scaling in between 0 and 1, which is an explained variation criteria, and this criteria is independent of the cumulative incidence. And if you plot this criteria over time, then you can see that the explained variation difference between the two models is not very high, but still, as with AUC, the exact score test performs slightly better than the multi-step examination. But of course, in fact, this is an ongoing work, so I cannot show you today the confidence range for this curve, but it is not very difficult to compute the confidence region for this kind of curve as soon as you have the previous result. So, to conclude, in this talk we try to propose a new testing approach to simultaneously compare dynamic prediction over all landmark time at which predictions are made, because in the joint modeling framework, we can make predictions at a lot of different landmark times. And we use a fully non-parametric methodology because to our mind this provides a fair comparison because it's non-parametric. And in fact, there is this very famous quote that essentially all models are wrong, but some are useful. And in the spirit, we use the joint modeling framework to develop some dynamic predictions. And our hope is that the model is good enough for prediction purpose, but of course, we do not assume that this model is perfect. So when we are evaluating the prediction accuracy of this kind of model, we do not want to assume any correct model specification. And for this result, we have some asymmetric results, and we have also done some simulations, and they are quite good results with sample size, so good coverage probability for the confidence regions. And as a perspective, we hope that this work could be used beyond the joint modeling framework, because as it's a fully non-parametric point of view, this could be useful to provide inference possible for comparing any kind of dynamic predictions. And for instance, we could compare the joint modeling approach to the landmark approach. And I think this is quite important because for some data, sometimes it's clear that the joint modeling or the landmarking is better than the other, but for some data, we do not know which one of the two approaches is the best. And of course, we have all our preferences, and sometimes we are not really fair. We choose one approach to the other, and this made me think about one of my favorite quotes, again about a quote from George Broad. It's statisticians like artists have the bad habit of falling in love with their models. And I think for prediction purpose, this is quite true. So we hope that with this kind of non-parametric comparison, we can provide some tools for